think people are mostly rolling in now, so I guess we should get started here.
Okay.
So welcome everybody to this week's edition of our Department of Statistics seminar series. So we're very excited to hear from Jelena Bradic from the University of California, San Diego today. She's one of the elite group of people, I'd say, that holds a PhD in statistics from Princeton University. I can't, did Princeton at some point have an official Department of Statistics?
Oh, we could speak about this for forever, but yes, John Tukey was there leading the department.
Yeah, right.
Passed away, Wilkes inherited, and there was some tension, and then it fell apart.
Yeah. So anyway, so we're really excited for this talk today, and her lab focuses on causal and robust machine learning. So with that, I'll let you take it away.
Thank you, Jonathan. It's a pleasure to be with everybody today. This is a good thing about Zoom. We get to meet each other virtually, and it makes it somewhat nice. My talk today will be on my ongoing work. I apologize ahead of time because it's sort of a work in progress. So I do want to encourage any questions or comments you have. I'm happy to stay after the talk and chat with whoever has questions. So I'd like to share with you my new work on dynamic causal learning and discuss a little bit about excursions in double robustness. I think your department has a very well established group that discusses and has studied treatment effects in dynamic times. Hopefully, I'll get to bring some new perspectives and some new, mostly theoretical understanding of what's happening there. I think we can all agree that data-driven decisions are spanning everyday life of almost each and every one of us today. So from continuous measurements of individuals' health on mobile devices or medical decisions being made as a result of that, to monitoring individuals' online presence or daily measuring of the economic or social policies, which is now ever more so apparent, I guess, at times of COVID. So studying the true treatment effect or policy effect in dynamic time, or when we have measurements over time, has become really complicated with lots of data that's available. And I hope that this talk and my work will bring in some new perspective to the literature in ways to construct confidence intervals, specifically about dynamic treatment effects in the presence of high dimensional observations. So again, dynamic treatment effects, confidence interval constructions, and high dimensional observations. I think the average treatment effect in the presence of multiple exposure times has been a long-standing problem of interest, and difficulties, both methodological and theoretical, in studying dynamic treatment effects have been numerous, right? So from the fact that previous treatments may affect the distribution of future confounders or mediators and treatment decisions and choices being made at each time. So I think I probably repeat this, I'm sure you all know, but in dynamic setting, traditional approaches, for example, such are generalized estimating equations or random effects models, are actually not guaranteed to lead to consistent estimation at all.
Yeah,
and there's
sorry. So we don't see the slides moving.
They're not yet moving. This is all introduction, for which I thought a conversation would go
sorry.
as well as having slides. Thank you. So this is really just motivation as to why we should study this problem from point of view of potential outcomes and causal inference, and not just immersed in some sort of more traditional statistical model. And there is many literature on this topic. So here are the slides moving, I think. Before I begin, I should probably mention that this is a joint work with two of my PhD students, one of which, Yuqian Zhang, is on the job market this year. He's really he has been a wonderful PhD student, super humble, excellent human being, and as you can see in the picture, enjoying San Diego weather. Okay, so before further ado, here is my outline of my talk for today. So I'd like to discuss a little bit about the setting of dynamic treatment effects initially. That would take a little bit of time, introducing notation, definitions of parameters and everything. And then I'd like to discuss what is it, dynamic double robustness. In other words, try to discover together with you or show you what I've discovered through my work. In the presence of high dimensional covariates, what is double robustness? Do we have it? What it is in the context of dynamic treatment effects, and what changes there, or does anything change? And I'd like to finish with numerical illustrations. I will have to apologize for not having real data because this is work in progress, but I will highlight numerical illustrations that we have. We've done quite a bit there as well. If at any point you have any questions, make sure to just speak up. I think I mentioned I'm not really good with chat, so Jonathan is helping with chat questions. Okay, so what are these dynamic treatment effects, and how would I like to define them? And keep in mind that my ultimate goal is to allow high dimensional confounding together with constructing confidence intervals. So here is a little bit picturesque view of the dynamic observations, or the particular dynamics that I am considering. I'm not entirely sure that you guys can see my mouse moving or not. I always forget that part. If anybody can tell me whether you see the mouse or not.
Yeah, we can see it.
Oh, okay, so I can use it as a pointer, basically. Okay, so the dynamics that I'll be observing, there are many ways in which you can set the problem up, but I think I've decided to work with a very traditional one, which is the bottom layer here denotes baseline covariates, and this would include any and all possible available confounders that are collected well ahead of any initial treatment decision. So I don't know, from medical imaging to genetics to anything really that can go here, from geographic and any kind of really data that you have about individuals. Then the second layer here denotes treatment exposure at the first time. So this is based on, this treatment decision is being based on baseline covariates. I think I'll use, instead of baseline covariates, covariates at time 1, but it's probably good to keep in mind that they are observed before the first treatment decision is being made. And then moving on to the next time period, we will observe covariates after exposure 1. These are measurements either of the baseline covariates, further down the time period, that are or have potentially been affected by treatment exposure, or perhaps what's done in a lot of survey data, this would be part of baseline covariates that are currently available, but perhaps additional set of covariates. So these two sets of covariates do not have to have the same features, the same dimensions, the same distributions. And after that, we also, of course, observe a treatment exposure at time 2. So this could be a doctor's decision to either change the treatment, to stop the treatment, include another treatment. And I'm not willing to make any assumptions yet whether the treatments, once you're treated, you always have to stay treated. No such thing is required. So switching on and off treatment is allowed. And of course, ultimately, we observe an outcome of interest. There is a little bit of a mathematical problem, or it wouldn't be a problem, but I guess our setting would allow also if you could observe perhaps an outcome at this time or after the first treatment exposure, that can easily be embedded in everything we're doing, but I chose to not do it. Just makes things a little more complicated to write down, but it's definitely allowed. So for this dynamics, this is, I should say, very traditional. I just want to make sure we go over it. It would be the same as in any other literature discussing dynamic treatments. And as is very common, I would say nowadays, we would use MSM models to study continuous outcomes in the presence of binary treatments. So the treatment variable is binary, and the presence of covariates. We allow both continuous and binary covariates, with a slight caveat that if we have binary covariates present, this will necessarily induce model misspecification in our, you'll see what models, I'll be precise. But bear in mind that in this paper, we want to study double robustness. So model misspecification is allowed, and you'll see what kind of results. Again, there's been a recent paper that I found really quite summarizing quite well this huge area by Babina, Rodzinski, and Jamie Robbins in 2019. I think it appeared in Biometrics, and kind of goes over really nicely the subtleties of dynamic study. Keep in mind that my goal here is to study or develop root and confidence intervals related to dynamic treatment effects. Okay, so here's another sort of view of the same setting, but maybe for those of you who are more inclined to have a network representation of the data. So the last endpoint here is the outcome of interest. These top layers are our treatment variables. The bottom layers are our covariates, and the natural time, I will use S to denote covariates at time 1. I will use A to denote treatment at time 1, and then covariates after the first exposure, there would be S2. Treatment similarly A2, and the outcome of interest is Y. I will assume this couple, again, I should say that the whole paper translates really well with more than 2 time periods, but for the illustration purposes, it just makes things a little bit more concrete. And maybe you don't need further motivation, or maybe you do, I don't know, into this problem. But although there have been a lot of recent results on double robustness in high dimensional setting, almost all of them, I'm inclined to say all of them, have been only done for 1 time period setting. I think this audience today is well aware that multiple time periods do not translate into 1 time period. There's a lot of identification issues. And in this work today, I want to highlight our results on dynamic, what we call rate double robustness, and a little bit about consistency, so double robustness in consistency sense. For those of you who are experts in low dimensional settings, perhaps it's a good time that I mention that model misspecification is or has different effects in high dimensional setting than in low dimensional setting. And by now, and hopefully by the end of the talk, you'll see why that's the case. Okay. So what are the setting or particular assumptions? And I'll begin with the causal assumption initially, and I'll discuss later the model setting. So the setup is really very classical in many ways. We are the two-dimensional vector A, which is A1, A2, but for short, just A, denotes our potential treatment, and Y of A is our potential outcome. So if we had a treatment little a, our observed outcome should be Y of A, but indeed, maybe we didn't observe that outcome, right? So it's an outcome of a person under the assumption that they have assumed treatment A. The observed Y necessarily does not match that pattern. So the average treatment effect is defined in a natural way. It's an average or mean difference between the outcome under the treatment path A or treatment path A prime. A prime may have some similarity with A, may not, but usually you can imagine A is just 1, 1, so you're treated in both time periods, and A prime is 0, 0, which means you're not treated in both time periods. But again, that's just one setup. And we will assume sequential ignorability, which really just implies that the outcome, well, there is some sort of conditional on covariates, say at time 1, the outcome Y is independent of the treatment at time 1, and then conditional on all of the, you can imagine a sigma algebra of observations at the time 2. So given all of the covariates and treatment at time 1, the outcome is independent of the treatment at time 2. The sequential ignorability is necessary for identifying theta as given the observed data. It has many names in the literature, such as exchangeability, sequential randomization, no unmeasured confounding, and many different things. We will also assume consistency, which means that the observed Y necessarily needs to be equal Y, where for the little a's, which are potential outcomes, we have plugged in the observed treatment variables. In other words, the treatment is completely, the potential is decided only by the treatment variables and not something else. For example, location is not allowed to be here. And classically, we have to assume positivity or overlap assumption. Let me introduce briefly the notation. So we use little pi to denote probability of assigning treatment in the first time period. This is conditional on the baseline covariates. And with rho sub A, we define the probability of assigning treatment in the second time period. Here we are conditioning on everything that's observed up to that point. So these are baseline covariates as well as covariates the second time point and the treatment at the first time point. Overlap really just means that for every fixed S1, pi of S is bounded away from 0 and 1, and similarly rho A. So these are really just propensity scores, as we like to call them in statistics, I believe. And they are needed to reweight our data in order to balance out the two treatment groups. Okay, so in this paper, since we want to study double robust estimation, really let me introduce what does that mean in low dimension. What is the double robust estimate? I'm pretty confident majority of you are well aware of this. So as I mentioned earlier, we want to study average treatment effects. It will be a little bit cumbersome to keep carrying the difference always, so I'll just focus for the time being on one of the treatment paths, and now focus on theta A being the parameter of interest. So theta A is the mean of, say, the outcome y under the treatment little a. And really, it's been a well-known fact that this parameter theta can be identified as an expectation of a double robust score. Sometimes this is called double robust representation of theta. The score is here denoted with psi of a, and it has, it's a little bit heavier notation, giving you a write-up for 2 time periods, but just bear with me a little bit here. I'll introduce everything. So remember how we had propensity score time 1 and propensity score time 2. WA will be the inverse probability weight at time 2. This necessarily implies a product of time 1 and time 2 conditional probabilities, and tau will denote inverse probability weight at time 1. You will see them here as weights. And what are we reweighting? We are reweighting residuals. What kind of residuals we'll introduce in a second. I know at the moment you don't know what is nu of A and what is mu of A, but you can imagine that I could hypothesize a model in which way y depends on covariates, and in many ways that's one of the nus and the mus. And if for a second we assume that we have access to these, we know what these nu and mu are, then the double robust estimator would be a very simple averaging where we plug in estimates for all of these unknown quantities, right? Okay, so what are these models? And with this, we're slowly finishing up the setup. The nu of A, as you saw on the previous slide, denotes conditional outcome model of the observed y given all of the information available before y. So that's including both treatments and both covariates at both time exposures, and includes, somebody calls also this sequential outcome regressions. It includes mu of A, which denotes another outcome model, but here a proper way to think about it would be an expectation, so conditional expectation of the new variable. So this response, if you wish here, or this model here, given covariates now and information at time 1. So we are projecting whatever model we had at the second time point into the first time point, given the information available at that time. It turns out, under the assumptions we made, is that both of these models have natural connection to potential outcomes, and I just briefly wanted to highlight that. So the nu of A is really an outcome regression, but of a potential outcome y. And similarly, mu of A is really simple outcome regression on of the potential outcome y on the first time period. The only caveat here, and why we need these nested models and a little bit complicated or sequential models to perform estimation, is that this model at the first time point is not identifiable. So if we were to just regress the observed y on the S's, which is baseline covariates, we will not get a consistent estimate of mu. So we really ought to regress this nu of A onto S and A1. So I think this highlights all of the modeling assumption that I wanted to go over. Any questions so far?
Yeah, nothing in the chat either.
Okay. I mean, there are classical, so to speak, problems that are related to these nested models in terms of identification and when is one model true and when is another model not true. And you can imagine what is very interesting, maybe I should highlight here, lots have been said on this topic, I should say, even in low dimension, is that presuming a model of this form in the second time point is somehow to a lot of statisticians very natural, and we feel comfortable, it's either this or not. But what happens with this first time period outcome model is rather intriguing in ways, in the following way. So even if the model, well, clearly, if the model at the second time point is wrong, the chances that this model is wrong are higher somehow, but there are no guarantees one way or another. And in the draft of the paper, which hopefully will appear in archive soon, we highlight some examples, some sort of, I won't call them trivial, but maybe a special example, special case examples where that could happen. But what is rather interesting is that even if we assume that this model by itself is true, so we forget maybe that this exists, it turns out it might not be linear in essence. So for example, we assume it's linear, but it turns out it might not be linear. So granted, chances that this model at the first outcome model at the first time point is misspecified are higher than any of the other models. Then in the later parts of the talk, I'll try to focus on what happens when there is some bit of misspecification. I should say that there is a very clear-cut example when these two models are compatible or hold at the same time. I'm talking about outcome models only, and that would happen if truly this outcome regression 2 is linear and outcome regression 1 is linear. And the way that the covariates at time 2 depend on covariates at time 1 is linear. But the other dependence on treatment variable could be very flexible. It doesn't have to be logistic or anything else, and it doesn't have to be linear. So if you imagine a time series setting or a Gaussian covariates, these two models would be very naturally satisfied. Of course, problems occur if S1, one of the S2s is binary, and S1, none of the S1s are binary. Then we necessarily are inducing some model misspecification. So I think studying model misspecification dynamic time is rather intriguing and quite difficult for the above reasons. Okay, so I think we're ready to immerse on what do I mean by dynamic double robustness and what are the challenges in high dimensions. Just before I say that, I will present, of course, an algorithm, and I'll focus on lasso estimator for simplicity, but maybe you just want to have in mind a little picturesque view of how this estimation goes about. So it goes backward in time. At the second exposure time, you will run an outcome regression, second regression at the second outcome. Sorry, outcome at the second exposure time. And that can be, you can imagine a linear high dimensional regression, because I'll focus on that. And then what you want to do, you want to regress the outcome of that. So the prediction coming out of that regression, you want to regress that. That would be your new outcome. So imputed outcome regression at time 1. And why imputed? Because we don't have access to the true model. We only have estimated model, which I called prediction. So you will have to run an imputed outcome 1 regression, and maybe it's also linear. Estimation of the propensity scores is sort of independent of the outcome regression. So you might run them backward in time or forward in time. It really doesn't matter. And for majority of the talk, I won't even mention how you estimate them, but you could imagine it's a logistic lasso estimator, for example, or any of your favorite estimators, really. Okay. So let's talk about what is the particular estimator that I'll focus on in high dimensions. First, I want to discuss outcome regression at the second exposure time. So this is denoted with the script nu. And I have a little star here to denote that this model may or may not be true. So the star denotes for me a working model. so to speak. And the true model is denoted with alpha only. So suppose that our working model is linear, and this U denotes an intercept as well as S1 and S2 that you saw before. And you can imagine that naturally alpha star, which is the working model for this regression, can be defined as such, as a projection of Y minus linear combination of the covariates and some parameter alpha. What is interesting here is that we need to condition on the exact treatment path at both time periods. So if we're interested in treatment at both time points, A0 needs to be 1 and A2 needs to be 1. And what kind of estimator we could define here? Well, naturally, since I would like to allow high dimensional covariates, and I think in dynamic times, it's really quickly the number of covariates grows exponentially with time. So lasso estimator seems like a natural choice, and I will denote alpha hat. There's a little subscript A here to denote the fact that this is conditional on a specific treatment path. The tildes here just denote that fact that I'm fixing treatment path, and I'm just looking at that down that arm, if you wish. Okay, so that's a very simple estimator. As I mentioned, the very interesting component of this setting is what happens with outcome regression at the first time point. Probably you've guessed it, since I mentioned linear models and linear working models, that I would like to assume a linear working model for this regression as well. And in order to do so, I have to first be able to identify what is the right model to look at, I guess, or the right variable to be called an outcome. And here, that's this U transpose alpha, which you saw earlier. I hope you remember. What did I do? Yeah, that's what we had before. So U times alpha. And you see that here U times alpha becomes our outcome of interest, and we want to regress at the first time period. What is a little bit hidden in this notation, maybe I should have expressed it differently. There's this little bar here. For the first time period, we don't really know what happened at the second time period. So we have to look at both people who got treatment at the first time period and treatment at the second time period, which is not unusual. Those were the ones that we estimated in alpha or used in alpha estimation. But now in the beta, we have to expand. We also have to allow people who, or include people who got treatment at the first time period but didn't get treatment in the second time period. So the bar just denotes that little difference there. And there's still an A to keep a track of. It should really be A1 because beta only depends on what happens at the first time period. But that would be a little heavy notation. So we try to avoid that. And I try to be a little bit more expressive here and highlight exactly which treatment path is considered for this estimation. But everything other than that looks like a very classical linear regression, except that the outcome here is imputed. So I'll use this word imputed lasso to discuss and relate everything to this beta hat. Any questions so far? So this is, I mentioned estimation of the outcome regressions. It goes without saying that propensity scores can be estimated using a logistic model plus a lasso penalty. I didn't write them out because they're in many sense very, very standard, so to speak. Okay, if I'm not hearing anything, let me introduce more generally. So it turns out that a lot of the studies of double robustness was hindering upon developing tighter results or results better than in the existing literature on imputed lasso estimator. So briefly, so this beta is just generic beta that denotes an estimator that runs a regression on estimated outcomes. So imagine that there are some outcomes Y, and we estimate them using Y hat. And we still want to perform, or we need to perform this type of imputed loss estimator. We would like to be able to develop some theory for beta hat that allows imputation error that's possibly dependent on covariate X. So I used X as a generic covariate here because I'm abstracting the problem a little bit because it's highly interesting besides the dynamic treatment, I would say. And we would like imputations to possibly depend on each other. So in other words, yi's are not independent across I, and yi hats depend on xi. So mathematically, that creates quite a bit of challenges, but we would like to obtain results of this imputed lasso that are adaptive in the way yi hat behaves. So if yi hat is a good estimator of yi, we would like to get a rate that decreases, and vice versa, right? If yi hat is bad, probably the rate of this lasso should not be very good, right? We haven't seen results like that in the existing literature, so we went on and designed them. And another little sort of trick is that we would not like this tuning parameter to depend on the imputation error, mostly because that's unknown. And when we run cross-validation, we have really zero control over how imputation error behaves. So it would be really nice if lambda here doesn't depend on the imputation. And I know this is a busy slide, but the theorem looks a little long. We were able to achieve fairly general results under, I would say, very mild conditions. So we are considering a sparse linear model only on the true outcomes y. We assume that there is some estimate imputation error, which we call delta m. M is just the number of samples here. And then we assume very classical assumptions on the design X, such as, for example, sub-Gaussianity in many ways, and restricted eigenvalue property. With those results, we were able to obtain high probability bounds on the estimation error of beta hat, which is the imputed lasso. And you can see that delta m factors into this first term. This expression here is probably what you see in many lasso papers, but I would say this one is rather new and in fact explicitly has the effect of the imputation error. Perhaps a little nicer to look at are the bottom results, where if we assume that the imputation error is little o of sigma, where this sigma is the variance of the true model, so it doesn't kill the signal that we're trying to estimate, then the estimation error that we were able to obtain for the imputed lasso scales of this order. This is very standard lasso type result, and delta m is the imputation error. So if the imputation error is smaller than the rate of the lasso estimator, we get the same rate as a lasso estimator. But remember, we're running an imputed lasso with it has many dependent factors going in. And we were able to achieve this result using we had to develop a sort of new, I would say, how would I call it, theoretical approach, proof. We had to identify, for those of you who know what a cone set is, to obtain finite sample prediction error bounds or estimation error bounds. The usual cone set would not work anymore because of the imputation, and we had to cleverly design a different cone set that would still allow us to obtain what we believe is maybe optimal rate, because if delta m is 0, we exactly go back to the usual lasso rate that matches in terms of conditions on tuning parameter, and the design matches those in the existing literature. Now that we have that,
about 10 minutes, about 10 minutes remaining.
Oh yeah, I think I explained the algorithm pretty well. I wanted to just highlight that in the paper we have not only developed results for lasso estimators. So we have general, we allow general nuisance parameter estimators. And I would like to encourage you to take a look in maybe 3 days time when it appears in archive, or you can email me and I'll be happy to share the draft. But this talk is only focused on lasso for simplicity. And here is our maybe main result. So it's good we have time, 10 minutes. I'm getting there. So if we assume that all of the working models are correct or are correctly specified, but remember they're high dimensional, then nonetheless, so despite the high dimensionality of our setting, we're able to achieve root n asymptotics for the AT estimator, theta hat. This, of course, will require some assumptions on the sparsity of the underlying models. So any little s you see here denotes sparsity of, remember we had 4 models, 2 for propensity scores, 2 for outcomes. And I would draw your attention to the second setting here. D denotes overall dimensional covariates. Sometimes it's only the first time period, sometimes it's the sum of the two, but you can imagine it's the sum of the 2 time periods. And what's called rate double robustness, it's a new term. I mean, I guess Jamie Robbins created a name for something that actually existed, I would say, in the literature, but I think it was still a useful name to denote this very specific high dimensional setting. And in dynamic, in one time period, what's called the product rate condition that's needed for double robustness. If you've seen any of the papers by, I don't know, Van Stelland and Dukes or Chernozukov and others, one time period has one product rate condition on the sparsity, but here you'll see that we have 3. So not 2, but rather 3. And 3 because of the imputed loss estimator. And if you remember, that depends, we go backward in time. So the estimation at the outcome regression at the first time point depends on the estimation error rate of the outcome regression at the second time point. And that's why we have 3 rates. But in general, really what it means is that both time periods, if looked separately, should be double robust by themselves. And anyways, that's all I have to say about this. This is a new result. And I think it extends really naturally to multiple time periods. And besides this, we were also able to allow model misspecification. So in one time period, model misspecification in terms of inference cannot be achieved by the previous scheme. In what I mean by previous scheme is that we would like to naturally use a very traditional broad estimator, such as lasso or maybe neural networks or whatever. But in order to achieve model misspecification for inference, one would have to design very specific nuisance estimators. And I have a paper that's called Sparsity Double Robustness that discusses that in one time period. That's still an open question in dynamic time, but we were able to at least showcase consistency rate that looks, as you can see here. Let me just give you a table view of that for the sake of time. This would be the rate of estimation of A to E. The axis means that that model is allowed to completely be misspecified. So it's not about sparsity assumptions, but really model misspecification. And we have, of course, bigger tables. This is just a snapshot, and you see that the rates actually change depending on which model is misspecified at what time, and whether there is overall 2 models misspecified, such as here, for example, when treatment variable models are completely misspecified, or when only one, which is outcome at time 1, is misspecified. Ideally, in order to achieve inference results, you would want to have something here that's root n rates, 1 over root n. you see that there's still sparsity factoring into it, which means either you have to assume very strict conditions on sparsity, or you have to design new estimators of the nuisance parameters. And I guess that's an open question that came out of our paper. Just really quickly, I think this table, I can share the slides, or we can discuss, after the official time has passed. I'm happy to share. This is a very classical setting with linear models and logistic models, and very nice sparsity assumption and Gaussian settings. What I'm trying to highlight here is that despite the dimensionality of the problem, which is listed here, we have really nice finite sample coverages. The overall sample size, even though it might look big to some of you, you should focus on N1 and N2 that denote number of observation at the treatment arm that we need to consider, remember. So for our second outcome, we have very restrictive setting, not just us, I mean, everybody does. And there, the smallest sample size really matters quite a bit. And for high dimensional inference, we considered lasso or group lasso or elastic nets, both in terms of propensities or outcome models, and they all behave rather similarly. The setting was not favorable to one or another anyways. And I'll finish up with maybe this setting where I plot a mean squared error, or the log of the root of the mean squared error of theta hat. Green color denotes oracle. Red and blue are our procedure, one using lasso estimators, one using elastic nets. And the dotted lines are the equivalent of our estimators, but not using a double robust score, using IPW score, an equivalent of a dynamic IPW score. And what you see is that the improvement we are gaining with double robustness, even when the outcomes are misspecified. This is the M8 denotes 8 simulation settings. So we've done quite a bit of those, and these are the misspecified outcomes at both time points. So propensities are the only ones that are correct, and this is the setting where IPW should be the best possible. But you see that there is still gain even when in that setting. For those of you that are in love with IPW, maybe I'm saying something terrible here, but I apologize. Anyways, really quickly, conclusions. Double robustness in terms of model misspecification, still not achievable, still an open question. Rate double robustness, we were able to achieve. What I didn't spend much time discussing for lack of time is that the results we obtain are asymmetrical. I glossed over 3 product rates and not 2. But the impact of the estimation error of the first outcome model at time 1 is more present than the other 3 models. And if you ever need some results on imputed lasso, I think our paper really highlights some good results, and I'll leave it at that. You can connect with me over email, and you can look at my website for any other inspiration. So thank you very much.
Yeah, wonderful. Thank you. Very interesting topic. To get us started with the questions and answers, we do have one question in the chat. So I'll read that question here. So the question is, what kind of imputation technique is suggested to use in the imputed lasso? And I believe this is in reference to slide 15.
Okay. We were using usual imputation, which was done by many before us, I would say, which is this one. So the outcome regression at the first time point, I think, is this the slide number 15? This is slide number 13.
Let's see here. Yunshu, I think Yunshu asked the question. Did you?
Am I the right slide at least? But let me say though, so here the imputation is very structured in the way that, in other words, it's the only one that works for MSM models. So I think our results, though, for the imputed lasso do not depend on the structure at all. So we just assumed y hat and could be anything that you might want to use. Because I believe imputed lasso appears in many different settings other than the one we looked at.
Okay, I have another question in here. I guess this is maybe a follow-up question. So are the simulation results in your work with lasso as good as the results in other literature using semi-parametric or non-parametric models to estimate the outcome?
We didn't do those yet. So if I understood the question is comparing lasso to other non-parametric methods. And I would say I do not fully know. So that's sort of an we didn't do that. It's a valid question to ask. Theoretically, the only thing we know is as long as the assumptions are satisfied, both should work really well. I do know because I looked at random forests, for example, separately, and they do not perform very well. And I'm not entirely sure what's going on there. I do believe neural networks perform quite well, showing that. Of course, it depends on what type of neural network. If it's a usual NLP, which doesn't have, it's not something ResNet or crazy CNN, then it's fine. But the minute you talk about ResNet or Res 34, 35, they have now a million names. They have more than 50,000 parameters. So it's safe to say nobody really knows what's going on. But I think that we need to, raise awareness that we need to understand these types of problems a little better as statisticians as well, because people are or will be using them, I'm pretty sure.
Right. Other questions?
Can I ask a question about the simulation table? So in your table, you include an oracle estimator, and it seems that the oracle estimator is perform worse than others.
No. Oracle estimator is green, right? Lower on the picture means better. Okay, but in your table, the number in the number system, like for example, the root mean square for the oracle is worse than the first. Okay, so maybe I should say I didn't have enough time. So you're right here. This oracle is, because it's simulation, right? I actually simulated both treatments for single individual, right? So I can look at this problem as not a missing data problem, right? And I can just perform a usual estimator, which uses all of the data. So that's what the oracle actually means. But it's not unusual for a lasso to have a smaller mean squared error prediction than the oracle estimator. Just this is the effect of super efficiency, I guess, of lasso, right? And my setting is truly sparse model that favors lasso. So I would say that's what we are really seeing. I don't think it's anything special. Okay, that's interesting. Thank you. Sure. But to highlight, this is a misspecified treatment setting where the green line is always below, and this is misspecified outcomes where the green line is always below. So the super efficiency, of course, doesn't happen when the model is misspecified. It's a good point. I think some people maybe read a little bit too much into that in practice, but it really depends on the model. It's a good question.
Hi, Jelena. Hi, Jelena, it's Ray.
Hi.
Talk. Yeah, I totally agree with the observation for the super efficiency. We have similar observations. And I just want to point out some related literature. I think your formulation is essentially a two-stage Q-learning from my understanding, except you don't really estimate the value function. And so in one of my previous work about high-dimensional Q-learning, where we focus on the So we work with a threshold
Mhm.
regularization. We work with a folded concave penalty. You're very familiar with that. And so our goal is try to deal with the non-regularity when you have a proportion of the subjects who do not have a unique optimal treatment. So that's why we developed a threshold version of the last or folded concave penalty, where we also establish the symptotic distribution and focus on the control the coverage probability for the parameter estimation that can be related with your work. And have another work about high dimensional A-learning where we really have double robustness, because A-learning have double robustness. So we deal with, we extend the results in Murphy 2003 in high dimensional setting. Also focus on the folded concave penalty. I just want to point that out. Also,
actually, it's included as a citation. Of course, I know pretty much all of your work. Yeah, so I believe, at least I remember better the Q learning paper rather than A learning. From my understanding, although the setting is very similar and the formulation and the model is very similar, but the problem is very different, right? You're estimating policy. You're learning the optimal treatment. You're not necessarily. You're not.
Procedure is related but different. But in order to show the consistency of the policy, we need to show the consistency of the parameter first. So in that part, it's similar with your approach. Well,
yes, but you are using, I believe, your rates are slower than what we obtained for imputed lasso, and your assumptions are stronger because I think you need to show model selection consistency.
Are you talking about the Q learning paper or the A learning paper?
Now maybe I'm mixing them up, but in one of them, and I remember that the tuning parameter depends on the imputation error. But I probably have to check the A. No, I'm talking about A learning. You're right, not about Q learning paper. I am talking about the A learning.
Yeah, that's okay. We can talk offline. So I just want to point that out. And also one comment to Yang's question. So I think, we have another recent work, which is just for one stage, but we work with of policy evaluation where the with continuous treatment, but we do use neural network to estimate the baseline effect, and the results turns out to be good enough. I can share the paper with Jelena if you're interested in the theoretical properties. That's really some new results, and I think it will have a good application.
Absolutely.
Yeah, thank you.
Thanks.
Okay, cool. Yeah, maybe this is a good place to end. Thank you very much for the talk again. And I believe you said you'll stay after a couple of minutes if anybody wanted to say hi.
Yeah.
Thanks everybody for attending. I guess I'll stop the recording here.